Namaskar everyone and welcome to today's video lecture. We are going to dive into an important topic in operations research and manufacturing, solving sequencing problems involving multiple jobs and machines. Specifically, we'll focus on a scenario with n jobs and 3 machines, using an extended version of Johnson's rule to find an optimal sequence that minimizes the total processing time. Our goal is to understand how to apply Johnson's rule to effectively schedule jobs through 3 machines in order to minimize the total time from start to finish. Johnson's rule is a method used in decision making for job sequencing problems. Originally, it was developed for 2 machine problems, but it can be extended to problems involving more than 2 machines by combining machines and reducing the problem to a pseudo 2 machine scenario. So first step is understanding the problem layout. Assume we have 6 jobs, each needing to be processed on 3 machines, machine X, machine Y and machine Z. Each job has a specific processing time on each machine. The jobs must be processed in the order of machine X, then machine Y, and finally machine Z. Step number 2 will be to prepare the data in a tabular format. Create a table listing all jobs and their corresponding processing times on each machine. For example, job A might take 3 units of time on machine X. It might take 8 units of time on machine Y, and it will take 13 units of time on machine Z. In order to solve the problems with 3 machines and n number of jobs, the first thing which we need to see is whether the problem can be solved using Johnson's conditions or not. So in order to proceed further, there is a condition which needs to be satisfied. So first of all, we find the minimum value out of the total values given for machine X. So for machine X, the total value is, the minimum value is 2. So minimum of X is 2 units of time, right? We find for third machine also, we find the minimum value. So minimum of machine Z is 8, that is job E. So we write 8 hours or 8 units of time. Then for the middle machine, we calculate the maximum value, which in our case is 8 units of time. The condition which we need to satisfy is that minimum of X should be greater than equal to maximum of Y, or minimum of Z should be greater than equal to maximum of Y. So for first condition, minimum of X is 2. It should be greater than equal to 8. Second condition is minimum of Z is 8. This should be greater than equal to 8. So in our case, the first condition is false and the second condition is true. So if any one of the two conditions or both are satisfied, we can proceed further. So in this example, we can proceed further and reduce this table into 2-step or 2-machine problem, right? So now we assume 2 pseudo machines, machine A and machine B. And the time which we calculate for machine A and B is such that machine A's time is equal to time taken on machine X plus time taken on machine Y. Time for machine B is time taken on machine Y plus time taken on machine Z. So let us calculate the table now. This is our original table, right? So for machine A, time will be For processing job A, it will be 3 plus 8. So 8 plus 3 is 11. Similarly, 12 plus 6 is 18. 5 plus 4 is 9. 6 plus 2 is 8. 9, 10, 11, 12, and 11, 12. Now similarly for machine B, this is 8 plus 13. So 8 plus 13 is 21. 6 plus 14 is 20. 4 plus 9 is 13. 6 plus 12 is 18. 8, 9, 10, 11, and 13 plus 1 is 14. So now we have converted, or we have translated, the original problem into a two machine n job problem, which can now be solved using Johnson's algorithm, right? So this is our table now, and we want to determine the sequence of jobs which will start from machine A and then they will be completed on pseudo machine B. So the rule is that out of the total values given in the table, we find out the minimum time taken for a job to be processed. So in this case, the minimum time is 8. Sorry, it is 8, right? And this 8 corresponds to job D and to machine A, right? So if it is machine A, then we will write that D job is to be carried out first on machine A, and we'll write it towards the left hand side starting with machine A. Now this column gets omitted and the matrix now consists of A, B, C, E and F. Out of the remaining values, we find out the minimum values. So now the minimum value is 9. And 9 also corresponds to machine A. So after D on machine A, C job will be processed. Now this column gets eliminated from this matrix, right? Now out of the remaining values, 11 is the minimum value and there is a tie in between these, in between the two jobs, right? So A job corresponds to machine A, therefore we can write A here, that it will be completed after C, and E corresponds to machine B, so we'll write that E job will be processed towards the end on machine B, right? Now this A column, this column and this column gets omitted. Out of B and F we need to find out the minimum value, so it is 12. This value corresponds to machine A, therefore we write that after A, F job will be completed. Now what remains is job B, so after this B will be completed. So this is our optimum sequence of jobs which will be performed on machine A and then it will be performed on machine B. Now remember that machine A and B are pseudo machines. So we converted the 3-machine problem into a 2-machine problem only and only to find out the optimum sequence. The next task is to calculate the total time elapsed, idle time for machine X, idle time for machine Y and idle time for machine Z, right? So for this we prepare a table in which the first column relates to jobs, second column is related to machine X, Y and Z. This is the sequence in which the jobs are getting processed, all right? So we always start with time 0. All right, so first the job processed will be job D, because this is the order which we have identified. So D starts at 0 point of time on machine X. It takes 2 hours. So the time out for process D or job D from machine X will be 2 units. Simple, right? Then at 2 units of time, when machine X is free from job D, it will process job C, and it will take 5 hours to complete that job. So 2 plus 5, 7. So the time out will be 7 units of time. Then at 7, A will start and it will get completed at 10. 7 plus 3, 10. F job will start getting processed at 10 units of time. It will take 11 hours. Therefore, the completion time will be 21 units of time or hours. At 21, B job will start getting processed. It will take 12 hours to complete, making it 33. So at 33rd hour, after 33 hours, E will start getting processed on machine X. It will take 9 hours, making it a total of 42 hours. All right. Now let us do the calculation for machine Y. So machine Y will sit idle. I mean, there will be no processing till the time D gets processed on machine X. So whatever processing on machine Y will start can only start at 2. That is after 2 hours, right? So D, after getting completed on machine X, will move on to machine Y at time 2. It will take 6 hours to complete, and it will be completed at 8th hour, right? Now machine Y has to process C job after it gets completed on machine X. So at 7, C is ready to move on to machine Y, but Y is at 7th hour, Y is busy processing D, right? So the processing of C on Y will start only once it has completely processed the job D. So it will start at 8, right? It will take 4 hours to complete, so it gets completed at 12, right? So A is ready at 10, but it will have to wait for 2 hours for getting processed on machine Y. So the processing of A will start at 12 hours. It will take 8 hours to complete, so 20, and so on. F will start its processing at 21. When it is free from machine X, it will take 1 hour to complete, so it becomes 22 hours. So at 22 hours, machine Y is free, but B will come out of machine X at 33 units of time, right? So the processing of B on machine Y can start only and only at 33 units of time, right? It will take 6 hours to complete, making it 39 units of time. Then machine Y is free at 39 units of time, but E is still not free. I mean, it is still getting processed on machine X. So the processing of E job on machine Y can only start at 42 units of time. Plus 3, 45. So at 45 units of time, machine Y will also be free. Now let us do this calculation for machine Z. So machine Z cannot perform its operations till the time D gets processed on machine X and machine Y. So it will take total of 8 hours. So after 8 hours only, you can start processing on machine Z. And it will take 12 hours. So 8 plus 12 is 20, right? Then this is 20, it is getting free at 20, so it will take C at 20th hour only. 9 hours, it becomes 29. Then it will take A only once it is free from C. So at 29th hour plus 13 will give you 42 units of time. Again, F is already free at 22, but machine is not free. So F will start getting processed on machine Z only and only after 42 hours. And it will take 13 more hours, making it 55 units of time. At 50, it is, and the B will start getting processed at 55 hours. Plus 14, it will get completed at 69 units of time. Then E will start getting processed only when B is complete, so 69 hours. It will start plus 8, 77, right? So the total time in which all the jobs gets processed on machine X, Y, and Z is 77 units of time. So let us make it in a proper manner. So this is our table, machine X, machine Y, and machine Z, and these are the times calculations based on the uh, processing time which each of the jobs takes on machine X, Y, and Z. So now we are required to calculate four things. Total time elapsed. Total time elapsed is nothing but it is the final time of the last job getting processed on machine Z, that is the third machine. So the total time elapsed is 77. Just a second. 77 units of time, right? Now let us calculate idle time for machine X. Now see, machine X starts its process at 2. At 2, the second process starts. Then 7, the second process starts. It is free by 10. So at 10, immediately F starts the processing. It is free at 21, so immediately B job is taken over. It is free by 33, and 33 immediately E is taken over, right? And by 42 units of time, it is completing all the jobs. But the entire time period of completing all the jobs is 77 hours. So after 42nd hours or 42 units of time, there is no work being done on machine X. So the total idle time for machine X will be 77 minus how much time? 42 hours or 42 units of time. So the total idle time will be for 77 minus 42 is 35 units of hours or units of time, whatever the time is in hours or minutes, right? Let us calculate idle time for machine Y. So machine Y will be free by 45th hours, I mean 45 units of time, but it will sit idle till the time the last job gets completed on machine Z. So it is 77 minus 45. But machine Y is idle in between as well. The first unit gets start, or the first job gets start processing on machine Y at time is equal to 2. It means that for initial 2 hours machine Y is idle, so plus 2, right? So let us check for the other jobs as well. So in the first case it is idle for 2 hours, then it gets completed, the job gets completed at 8, it starts the another job at 8. This job gets completed at 12, it starts the another job at 12. Then the third job gets completed at 20, it starts another job at 21 hours, right? So 21 minus 20, so 1 hour more it is free, idle, right? Then it gets completed at 22nd hours, 22 hours, and it is starting the next job at 33 units of time. So 11 hours it is sitting idle. 33 minus 22, right? It gets completed at 39 hours. Then the last job gets processing at 42 units of time. So 42 minus 39, 3 hours it is idle. So total idle time for machine Y will be 77 minus 45 is 7 minus 32, right? 32, 33, 34, 35, 35, total is 49, right? So 49 units of time is the idle time for machine Y. All right. Now let us calculate idle time for machine Z. So machine Z will complete the process at 77 hours. So 77 minus 77, obviously it is 0. Let us check the idle time over here. In the first case, the first job will get started at 8 units of time. So till 8 hours, your machine Z will remain idle, right? Now let us check for the other jobs as well. So the first job gets completed at 20, it starts at 20. Gets completed at 29, next starts at 29. It gets completed at 42, next starts at 42. It gets completed at 55, starts at 55. Gets completed at 69, starts at 59. So in between there is no idle time. So the idle time for machine 8 is 8 hours or 8 units of time. Understood? So today we have learned how to tackle a complex problem of job sequencing with 3 machines by cleverly transforming it into a simpler 2-machine format using an extended version of Johnson's rule. This approach can be crucial in settings like manufacturing and production to optimize the operational efficiency. Thank you for watching this tutorial. I hope you now feel confident in applying Johnson's rule to solve sequencing problems with multiple machines. Thank you.